If you remember back in about 2009, 2010, we had an H1N1 pandemic, and a number of stages were regularly reported as we progressed through them. Interestingly, with respect to COVID-19, we didn't have the same discussion, and I think that's probably because the World Health Organization may have been taken off guard here with the emergence of the pandemic, and I'll talk about that in a second. The other factor is perhaps citing these phases incited some fear in the public as well. Either way, let's take a look at these phases. Phase one refers to the fact that there's no animal pathogens circulating among humans. Now, people track viruses, people track emerging disease. For example, Nathan Wolf, I've asked you to take a look at some of his material. And we know that from time to time, in the same way that humans see outbreaks of disease, the same thing is true among animals. When we're talking about an animal epidemic, we refer to it as something being epizootic. So that's an outbreak of disease among a non-human animal population. Now, phase one then, no animal pathogens are circulating among humans. Phase two refers to the fact that an animal pathogen now has caused a human infection. One of the things that's happening here is we're looking for further mutations. So just because a human got sick, it doesn't mean that a human's going to transmit that infection to another human. We need mutation to take place. That virus or that bacteria needs to pick up the right genetic material to be able to transmit to individuals, for example, through airborne droplets. So the R naught or RO, and I'll tell you what that means in a minute. That refers to the level of infectivity. We'll have a definition in a second. Phase three, this refers to small clusters of outbreaks among humans, and there's limited human-to-human transmission. I suspect we probably heard of COVID-19 around phase four. There was human-to-human transmission. It was occurring at community levels. We have these community level outbreaks. Phase five. This refers to human-to-human spread of a pathogen in two or more countries in a WHO region. A WHO region, for example, would be Asia, North America, Europe. They're all separate WHO regions. So as soon as we see, for example, a pathogen in two or more countries in a WHO region, well, let's say South Korea, Taiwan, and China, we're in phase five. As soon as that begins to move, say, to Europe, and we see infections there, now we're in properly phase six, and we're at a full-blown pandemic. So phase six refers to human-to-human spread of a pathogen in another country in another WHO region. In other words, we're seeing it in Asia, and now we're starting to see it, for example, in Europe or in North America. Let's move to the next slide. With respect to COVID-19, we probably should have got to that phase five and phase six a little bit earlier than we did. It wasn't until March 11th that the World Health Organization had officially identified a worldwide outbreak of disease or a pandemic. Problematically, this was first identified in China, and that information was not provided to the World Health Organization in a timely manner. And here we have a discrepancy between documents. So the World Health Organization, they have the documents that China provided them, telling them that there were a few outbreaks, but there really wasn't a serious issue. However, the internal documents that have been leaked within China suggest that they knew that there was a serious problem, and they were taking radical steps to deal with this quite quickly. So the reports of the severity of the new disease, they weren't reported to the WHO by China until late January. Now, scientists have looked at what would have happened if we began to lock down earlier. What if that information had been conveyed, and within a couple of weeks of seeing a rapid spread within China, what would have happened on a global level? So what the modeling suggests is that the World Health Organization, in delaying this pandemic, if we had identified it earlier, it may have reduced global morbidity by 80%. In other words, the infections would have been reduced by 80%. Now that's really significant. We reached, as pointed out, pandemic phase 6 on March 11th. That's when the World Health Organization had identified this. We began to engage in lockdown procedures. However, from a medical anthropological perspective, looking at that biocultural approach, our behavior and our culture also prolonged what was taking place. We didn't act fast enough. We got messaging that had pointed out that even though we have an emergency, we've defined a pandemic, and we're going into lockdown, it's okay to travel. We shouldn't have been traveling. That messaging should not have been provided. Let's run through a few terms here that I've been using and that I will be referring to. So number one, when we're looking at disease, it emerges within a specific geographic region. That's what we want to call an epidemic. So we have a local or a regional outbreak of disease. This is approximately phase 3, that community outbreak. Once we define a pandemic, we're saying that this disease, it is spreading on a global level or has the potential to spread globally and impact everybody around the world. Eventually, we reach a state where disease has situated itself firmly within a population and it never goes away. For example, the common cold, seasonal influenza, that's always circulating. We're not able to get rid of it. The only way that we can, in fact, get rid of it is through an aggressive vaccination campaign. So endemic means within a population. Morbidity, I've referred to morbidity. This means the incidence of disease, the distribution of a particular disease. So how many people are infected with SARS-CoV-2, for example. Right now, at the time that I'm discussing this, we're in July when I'm recording this, and we're at about 8.5 million individuals globally. That's the morbidity. As for the mortality, this refers to the fatalities caused by the disease, and we're at about 500,000 deaths currently globally. I've used the term zoonosis. This word is derived from a Greek word, zoon, which means animal. Look for that similar feature there, zoo. So this is an animal-derived disease. And what we're going to find out in our course, I'm going to give away a little bit of now, 61% of the diseases that impact us, that make us sick, are derived from animal sources. That's a lot. And what we should be thinking about is, well, how does that happen? Why have animals affected us so adversely? I think COVID gives us a good example of that relationship when we're disrupted balances, and also the role that humans have played in this as well. Now, while this disease may have emerged in China in a wet market, that's only part of the problem. We have also played a role in increasing the morbidity and the mortality in a lot of situations. For example, if we look at this resurgence that the United States is seeing right now as we were moving into July, I think they've said 1 in 10 individuals in Arizona are infected. This is because they've let down their guard. They're not following that distancing measures, the physical distancing. They're not wearing masks, and we're seeing an increase in those cases. We're moving into a second wave. When I use the term reservoir, what I mean is that the animal that the disease is indigenous to. So the coronavirus that we're looking at now, for example, it came from bat populations. The bats are the reservoir, the natural reservoir from which the disease has emerged. In addition to that, we have a term spillover. This refers to a process or an event where the natural reservoir has infected a new animal, whether it's a pangolin, for example, or a civet in the case of SARS in 2003, or with us, perhaps, as noted, the pangolin. Finally, I've referred to the R0 or the R0. This refers to the reproductive value of the virus. So if we look at a 4.1, what does that mean? Well, that means for every one individual, they're likely to infect for other people. That's where COVID is pretty much bouncing around between the 4.1 to as high as 6.5 currently. Now that's pretty infectious. That's more infectious than Ebola. Ebola is around, I think, about 2, we'll say. The R naught is around 2. In contrast, measles, that's really high. That's in around the high teens, the mid to high teens. So this is infectious. It's not terribly infectious, but if it continues to mutate and if we get other recombination events, now we have a potential problem. Let's move to the next slide. So let's gain an appreciation for the pandemic currently and COVID-19. So when we look at the agent that's responsible for the disease that's been named COVID-19 is the SARS-CoV-2 virus. And as for the natural reservoir or the zoonotic reservoir, this is traced to bats in the Yunnan caves in the Yunnan province in China. And this was first discovered through some research when they had found a new cave system, the Yunnan cave systems. They had taken some samples from the bats in that area. Virologists were interested in seeing whether or not there were any new diseases there. And the virus, it was pretty much shelved until the emergence of COVID-19. They looked back at this collected sample, TARG13, and they had identified at least a 97% genetic similarity. In other words, in all likelihood, this is where the virus came from. This is the ancestor, which we think is probably about 40 years old. The spillover, we're still working on this. It could be a result of direct spillover from bat populations, as pointed out. It could be the wet market. We're not sure. Only time will tell. The couple other facts about this virus, it's well adapted at entering the human body through its spike protein. So on the right hand side, we could see those spikes on the surface of the virus. And what that does is it attaches to the ACE2 receptor. So there was a specific mutation here that allowed it not only to attach to our ACE2 receptor, but we're finding that a lot of animals can contract this. And that does make it worrisome, ranging from dogs to cats to birds. More recently, mink populations, they farmed, the ones that have been farmed, they have contracted it, they've spread it to other animals, and that farmed mink population have to be culled. So after this virus gets into the body through that ACE2 receptor, what ends up happening is it begins to replicate itself. Number one, it starts to replicate itself. And if there's another coronavirus in there, there's a potential that it will engage in a process referred to as recombination. So in other words, it'll exchange genetic material with other coronaviruses and create potentially more harmful strains or possibly weaker strains. So we get these new virions. If we look on the right-hand side, the bottom image, they've been produced as a result of this first virion getting into the body. We have possible recombination, and then it's shed. In other words, we know that it can be transmitted through fecal matter, for example. This is why hygiene is really important. Or it can be transmitted through droplets. And as pointed out in our textbook, it's even possible that this could be transmitted through sexual contact as well. Let's move to the next slide. So to understand this process, we need to refer back to some of our discussion on evolution. So if we ask the question, what needs to happen for a microbe to infect a new species, for that spillover event to take place, for example, from phase 1 to phase 2 or phase 3? The answer simply is biological change. There needs to be some sort of a shift. There needs to be mutation taking place within this virus, allowing it to become more efficient at attaching, for example, to the ACE2 receptor. Let's move to the next slide. Now, I want to give you an example here. Thinking about infectious disease and moving, for example, from phase 1 to 2 or phase 2 to 3. What needs to take place, as pointed out, is some sort of a mutation. What I want you to think about is an older computer versus a newer computer. And we have an image here, for example, of that DIN type of adapter on the back of a computer on the left-hand side. And then we see a USB. There's absolutely no way that that USB is going to plug in to that DIN system, that input there. In other words, if we imagine that DIN system, that computer, as the human body and the virus as the USB, without the right tools or the right anatomy, so to speak, it can't plug into us. This is true, for example, if we look at HIV. HIV gets in through the CCR5 receptor. That's how it gets into the human body. Interestingly, the human body, and we're not sure exactly when this has happened, but it has mutated in a way that 18% of Europeans are immune to HIV. In other words, they can't get it. What's happened in their body is that receptor, that CCR5 receptor, has mutated into something that we refer to as CCR5 delta, that triangle there, delta 32. So that's a receptor mutation. And as a result of that, that virus can no longer plug into the human body. So these are the types of changes that were taking place. These are random. It's about natural selection. So in the end, when we look at transmission, it's not that easy. These major infections that we're looking at, they're zoonotic. And honestly, transmission between different species, it's rare. This isn't something that we're seeing all the time. New diseases are emerging, for example, among animals, but often it just doesn't have the right genetic material to infect another animal or a human for that matter. However, when we see mutation or mutation is introduced, this allows for the possibility of these new infections gaining that genetic material that they could plug into that new host's biology. And that's where we are with the coronavirus. We have an incident that's allowed for spillover, and it had the right genetic material that it didn't stop with one or two people that had come into contact with what animal was carrying that particular virus. They picked up the virus and they were able to transmit it to other humans. So that tells us that it had sufficient biology to be very efficient at moving through human populations. Now, this has led to some conspiracy theories. Some people say, what are the odds of that taking place? And it's led them to the idea that the coronavirus, the SARS-CoV-2, was manufactured in a lab as a type of bioweapon, and it escaped. Now, science, and it, you can look at good science. That's where I would suggest you look, not at the conspiracy theories out there that are regurgitating this propaganda. There's absolutely no support for that. And we want to be very cautious about any of those ideas, because on the psychological level, we have to understand that those ideas do a lot of harm. And I think it's a type of, or a form of terrorism. It does terrorize populations. It creates fear and quite often causes us to act in ways that just do not support human health. So let's stick to the science, okay? Let's move on to the next slide. Let's take a look at some of the mechanisms or modes of transmission. In other words, how disease gets around. On page 42, depending upon what edition you're using, you're going to find a table that talks about two different types of mechanisms of transmission, direct and indirect transmission. Let's run through these quickly. Direct transmission refers to touching, sneezing, kissing, or sexual intercourse. In the case of SARS-CoV-2, sneezing is one of the ways that it can be transmitted. So the virions or virus particles, they're trapped up in respiratory droplets. And when somebody sneezes, you can be infected. Kissing would be the same thing. Saliva, it contains virions as well. And as pointed out, some research is indicating that perhaps semen also will contain enough viral matter or virions to infect an individual. Indirect transmission, vehicle-borne, refers to some sort of inanimate object that's responsible for the infection. In other words, take a glass that somebody has sneezed on, or if somebody didn't wash their hands after they went to the washroom and they have SARS-CoV-2, COVID-19, they have that virus, and they've touched the edge of the glass, and you drink it, now an infection can occur. Problematically, when we look at feces, this is another way that viruses are being shed. And because we haven't come into direct contact with a person's feces, but rather it's been done through a glass, we refer to this as vehicle-borne. And the term for that type of transmission or those particles, we call it fomites, something that's shed. In contrast to vehicle-borne, we have vector-borne transmission. This refers to the spread of disease by insects. So, for example, malaria is spread by mosquitoes. Trypanosomiasis is spread by the tsetse fly. There's no evidence that COVID-19 is spread through insects. And this might be related to the amount of virons that you need. At the height of HIV, people were worried about mosquitoes transmitting HIV. And while they can contain those virons, there's just not enough viral matter, as our textbook points out, to infect an individual. Finally, we have indirect transmission, airborne. And this is where somebody has sneezed in an area, for example, and we have suspended airborne particles, or somebody has flushed the toilet and some of that fecal matter has been aerated into the air. This can infect an individual as well. Let's move on to the next slide. Okay, I want to review a couple of ideas. If it's review, that's a good thing. If it isn't, that's also a good thing that we're talking about it now. And I've caught it because I am asking you to write about how disease is just as much cultural as it is biological. Now, what does that mean? Because disease, we said that it was caused by viruses, bacteria, protozoa, worms or helminths, and prions. Those are our categories of infectious disease. So how is this cultural? Let's start off with looking at this on the biological level. The individuals that are interested in studying the distribution of disease, we call them epidemiologists. So they're interested in distribution, patterns of morbidity, and, for example, mortality. Okay, so in other words, how much disease, for example, how many cases of COVID are out there, that would be morbidity. And if we're interested in how many people have died as a result, we have mortality. Okay, so our different categories. The distribution of any disease, it is infected or affected by culture. So human behavior, it plays a role in the distribution of disease. And this is also influenced by our culture as well, or our beliefs. So in addition to this group that we refer to as epidemiologists, we're also interested in something that we call cultural. There's my dog whining away. Cultural epidemiology. She doesn't seem to be too excited about this topic. Okay, so that's what we're going to be talking about, cultural epidemiology and the ways that human behavior and culture influence disease. even though that disease might be caused by a virus, bacteria, or protozoa. So in particular, we're seeing this with SARS-CoV-2. That's the virus. So that's not cultural. Okay, the SARS-CoV-2, that's a virus, that's bacterial. However, in contrast to SARS-CoV-2, COVID-19, let's write that in there, COVID-19, this is shaped by culture. So this is also biological, and we had a word for this as well that we've used already, and cultural. So we get this biocultural approach. Now, how's that the case? Well, we've talked a little bit about this as well, and we'll look at it a little bit further, but I'll give you a quick example. COVID-19, it's shaped by its R naught factor. So here R, we've got a 0. This is the basic reproductive value. When we look at COVID-19, the biology of this, it has a value of about R, we're going to say on average 4.5, in around there. So that means for every one individual that has contracted COVID-2, 4.5 individuals are going to be affected. The other thing that affects distribution, and we're seeing this among a number of different populations, for example, is economics. Let's write that in here. I've lost my O. My dog's sad about that. Let's bring that back up. Economics. Now this tells us if we can look at the distribution of disease and we can see that it's shaped based upon the amount of income that an individual earns, that health is being mirrored by wealth, or that we see a mirror reflection of health and wealth, we know that it's not purely biological, that this also has something to do with our culture, it has something to do with economics, it has something to do with our living conditions or human behavior. So I want to run through a couple of examples in the segment to give you an idea of how disease, something that's biological, virus, bacteria, protozoa, worms, or prions, that could be influenced, or the distribution could be influenced by culture. Let's move to the next slide. So our textbook talks a little bit about 1967, the summer of so-called love, and the emergence of a virus that we call the Marburg virus. It causes a type of hemorrhagic fever. In other words, an individual literally dissolves from the inside. Now, there's no question that this is a biological thing. However, the emergence of this disease has cultural circumstances. What are they? Well, a few facts about Marburg. Initially, in Berkeley and in Germany at Marburg, so Berkeley, California, and Marburg in Germany, they received shipments of green monkeys. Now, those monkeys in Germany, they were infected with this Marburg virus. So the researchers at Marburg, as a result of studying monkeys in a laboratory system and the ways that they handled those particular monkeys, they exposed themselves to infected saliva. Now, the saliva and the transmission, that's biological, but the circumstances that led to that event where an individual was infected with Marburg, that's purely cultural. So the Marburg researchers, they developed fever, rash, and hemorrhaging. So we see this viral transmission, as pointed out, that's occurring through fluids during research. So we're seeing two things happening here. There's the biology of transmission, but there's also the factors that led to that transmission, coming into contact with the fluids, our practices, our safety practices, even the PPE, for example, that was used at that point of time. So we see a biocultural relationship here. We can't look at Marburg and say culture didn't influence the emergence of this particular virus. It did. Let's move to the next slide. So, in addition to just the biology of a particular virus and the genetic code that has and how it could attach or gain access to our bodies, for example, through that mutation, that random process that we had talked about in evolutionary biology, we have to understand that nothing exists in a vacuum, and the environment and human behavior play a role in shaping patterns of disease. So let's keep that in mind and let's move on to the next slide. So in our textbook, we talk a little bit about hantavirus in South America and in the United States of America, four corners. And here we see a relationship not only between weather, the emergence of nuts, and an abundant amount of mice and rodents and spreading this hantavirus, but humans also played a role. So asking the question, what role did the environment play in the emergence of hantavirus in South America? What's been correlated with that is the El Nino event. El Nino produced heavy rains, and as a result of those heavy rains, there was an abundance of peanut nuts. And because there were more resources, we had a proliferation or an abundant amount of rodents reproducing. There was a lot of them. Now, those rodents were the vector for that hantavirus. It was transmitted in their aerosolized urine and in their saliva. Now, the thing about this is we also know that we play a role in that El Nino event as well. So everything here is starting to come together where at one point of time we thought that we had different types of entities or phenomena out there. We had the environment, we had disease, we had human behavior, and now what we're starting to understand is everything is in fact interconnected. And if one domino falls, the others are closely aligned enough as things are in nature, it's going to have that domino effect and it's going to put into a series of events. Let's move to the next slide and look at another example. I've talked about piggeries in Malaysia already, and here we can look at the Nipah Valley virus or Nipah Valley fever and ask the question, what role did pig farming play in the emergence of Nipah virus in Malaysia? And the other thing that I want to point out is the economy also plays a role in the emergence of this disease. So what had ended happening as the economy started to boom in the 1990s and populations begin to increase, the need for farming becomes greater. So farmers begin to encroach or move into different ecological niches. So what we start to see is a blending of different types of farming where we have piggeries and we have fruit farms, and they're also moving in or encroaching into areas where there's a lot of bats. Now, pig farms, as pointed out, they're being established in areas where the flying fox bat is indigenous. And what this provided was an opportunity for a viral spillover from bat to pig to human populations. So what ended up happening as a result of human behavior and the way that we were doing farming in Malaysia at that point of time is the bats would come in to eat fruit. They'd eat part of the fruit, it'd fall to the ground, pigs would come by and they'd eat the fallen fruit. And in doing so, they would ingest some of the bat saliva that was on it. Or the bats would excrete. The pigs would come down, they would eat that feces, and they would pick up the virus. Now, humans, either coming into contact with fruit that bats had been on, or the pigs, and they didn't cook them enough, or they came into contact with pig saliva, they picked up the Nipah Valley virus. So this kind of emergence of this disease in the 1990s, it can't be understood properly. We can look at the distribution, how many people got sick, how many people died, that's fine. But unless we look at it from a cultural epidemiological approach, we don't understand really why the disease emerged and how we impacted its emergence. Let's move to the next slide. Before we wrap things up, we're going to talk about some famous vectors, and we're talking about famous insect vectors here. A vector, in this case, what we're talking about is something that's responsible for transmitting a pathogen. All right, we got that. Let's take a look at some examples. Here we're looking at by far the deadliest animal. It's an animal on the face of this earth, the mosquito. The mosquito's responsible for transmitting a range of diseases from St. Louis encephalitis to dengue to malaria, West Nile virus. They do not transmit HIV, as pointed out in our textbook. While they do carry virion particles, there are not enough particles ingested, and what's ingested into the individual, it is eventually digested. Okay, so we don't need to worry about that. Some people have in the past, but there's a variety of different types of mosquitoes. And as, again, referring back to that idea of disease being cultural, as we continue to create situations that lead to global warming, climate change, we're creating situations that are ideal for mosquitoes. And this really, we've had a long history with mosquitoes, and they really became a problem when we started augmenting the ecology of an environment through, for example, what's referred to as milpa or swidden, slash and burn technology, where you'd slash the vegetation in the fields, you'd burn it, and you would engage in a type of shifting cultivation. So what would end up happening historically, and this was an early innovation in farming. So we have our village, for example, here in the center. And what we would do is we'd have a plot of land over here that we would farm. And eventually you need to let that land sit fallow because you've deprived it or you've depleted all the nutrients. So you'd engage in slash and burn, and you'd shift that, and you'd do your farming there. And then eventually this soil would become depleted, and you'd have to shift your cultivation to a new plot of land where you do your farming there, and then eventually depleted. But by the time this was depleted, what would be happening in this type of circle is we'd start to get new growth here, right? And you'd go in, you'd engage in that slash and burn, or what's referred to as swidden or milpa. And you'd engage in the slash and burn, and you'd be able to shift your cultivation to this new area. And in doing so, people could live in one place. They were able to engage in sedentary living. The problem was when each of these areas were laying fallow, right? There were areas that would collect water. And one of the things that our health boards tell us is we shouldn't keep tires around where water collects because that breeds mosquitoes. Right, we get mosquitoes in there, and the mosquitoes, they have a flying radius of about 2 kilometers. So this type of environment, this type of augmentation of the ecology of that we're living in, this brought mosquitoes into regular contact with humans, and then we see the morbidity and mortality, for example, of malaria increase. So here's one deadly vector. Let's move on to the next one. So mosquitoes, the deadliest animal on the face of the earth, and by far we're going to have to argue that fleas are responsible for the single greatest pandemic on the face of this earth as well. Now, fleas, they're responsible for transmitting or vectoring what we call bubonic plague. Now, bubonic plague is caused by a bacterium. That bacterium is called Yersinia pestis. As pointed out, they're kind of a middleman in this epidemiological exchange. So we get rats. They carry Yersinia pestis, and it also makes them sick as well. So they're not the natural reservoir. We're not sure what the natural reservoir was, perhaps marmots, but either way, rats, they carry Yersinia pestis. And fleas, they like to live with rat populations, and they drink their blood. So when the flea drinks rat blood, it picks up Yersinia pestis. Now, when the rat populations, when they die off, and you have to understand that bubonic plague is an issue when we have civilization and large populations. Rats are living with people. The rat populations die off. Fleas, they begin to look for a new blood meal. And if humans are around, they're a great choice. And they drink our blood. The problem is if they're infected with bubonic plague or Yersinia pestis, here in their gastrointestinal tract, I'll switch over to my highlighter, in their gastrointestinal tract, right about here, they get a clot. And that clot is caused by the bacterium. So what ends up happening when they drink our blood, it goes in, it gets blocked, they regurgitate, and the Yersinia pestis is regurgitated back into us, and we pick up the bubonic plague. As pointed out, perhaps the single greatest epidemiological episode, was caused by fleas, this vector. In Europe, upper estimate 60 million of the 80 million people that were alive in Europe from 1347 to 1351 died. So while COVID-2 is pretty rough, we're seeing this increase on a daily basis. We're not seeing anything like what took place during the 1300s with respect to bubonic plague. Let's move to the next vector. Lice can be particularly embarrassing, especially if you or your child has been sent home with what's referred to as pediculus capitis. Pediculus capitis, this is essentially head lice, right? That capitis, head lice. And that's not deadly. In fact, while it's embarrassing, pediculus capitis, this is really not related to being unclean. It's related to a clean environment. And one of the best ways to keep your child or yourself from getting pediculus capitis, head lice, is by having product in your hair and not washing it all the time. In contrast to pediculus capitis, we have pediculus humanus. And pediculus humanus, it's responsible for typhus. And typhus, scratch typhus, it's actually very deadly. So what ends up happening here is the louse isn't directly responsible for transmitting the bacterial infection here. Instead, in their excretia, when they're on top of us and they excrete, that stuff makes us itchy. And because it's itchy, what do? We scratch. And that scratching motion is responsible for causing typhus. Now, pediculus humanus, this is something that we see in unhygienic, dirty areas. Okay, let's move on to the next vector. We're seeing an increase in Lyme disease in Ontario in recent times, and the vector for Lyme disease is the tick. Now, what's the relationship here? Humans, we're playing a role because we are encroaching into environments where there's a lot of mice, white-footed deer mouse, deer, and ticks. And one of the things that they have in common, at least from an environmental perspective, is wooded, tall grasses, right? So that's the environment. Now, how are we encroaching? One of the ways that we're encroaching, more people are out, especially now, hiking, for example. So we're hiking in these areas. In addition to hiking, we also see a lot of homes being built that back onto wooded and grassy areas. That's highly desirable. And in doing so, we're moving into an area where this disease moves. So this is the way it works. We have mice, and they are the NR, or the natural reservoir for Borrelia burgdorferi. Long word. Borrelia burgdorferi. Now, what ends up happening is the tick is looking for a blood meal when it's a nymph, and that blood meal is a mouse. Later on, as it continues to grow, and it's picked up this Borrelia burgdorferi now from the tick, this bacterium, this bacterial infection, it spreads it to deer. When it gets a blood meal from a larger animal. Now, if a human's in the environment, so this tick's looking for a larger ungulate, but if a human happens to be in the environment, no worries. As far as the tick's concerned, that's a good blood meal as well. Now, what will happen is this tick will bury itself in the back of one's leg and the neck, a variety of different areas, and it'll hang out there and just consume blood. In fact, they said if we compared it to a human, it would be like a human going into somebody's backyard with a straw pretty much and drinking up the entire in-ground pool. They're taking up a lot of blood for body size. And then once they're full, they just kind of fall off and they hang around until they're hungry again. And then they jump on another individual or deer and continue to spread Borrelia burgdorferi. Now, the thing to watch for with this Lyme disease is you end up getting a type of rash. It's called a bullseye rash, and it's exactly what it looks like on an individual. It has that bullseye shape, and at that point of time, one knows that they've definitely been infected with Borrelia burgdorferi. Let's move to the next slide. Okay, so hopefully you're getting the idea of what a vector is and some of the more significant vectors in human history. The tsetse fly that we're looking at here, it's responsible for transmitting something called trypanosomiasis, and this is African sleeping sickness. Now, this doesn't actually cause one to sleep. This is more of a euphemism, African sleeping sickness. An individual eventually becomes quite lethargic, goes into coma, and dies. So, yeah, not quite sleeping. So another significant vector in human history. And we're also seeing an increase in morbidity and mortality in recent times, and that's being affected by human culture, our behavior, deforestation. So that deforestation, it's creating ideal breeding grounds for the spread of trypanosomiasis. All right, let's move on to the next slide. Okay, so the last vector, and there's a lot of vectors out there. The last vector I want to talk about is a tumbu fly and something called myiasis, because this is just absolutely horrifying. The tumbu fly, what it does is it grabs a smaller insect, a biting insect, for example, a mosquito, and it lays its eggs on that mosquito. And it does so on the mosquito's proboscis. So thinking about a mosquito, right, you got that mosquito head, and it's got that long needle that it injects, that it gets our blood from. That's the proboscis. And now you've got this larva, this tumbu fly larva laid on it. And it gets some blood, and in doing so, that larva is kind of impregnated into the skin and underneath of the skin. And that creates the ideal breeding ground for the eggs. They eventually hatch, and you get this eruption of worms, maggots. It's absolutely horrific. So the tumbu fly, you can imagine historically, quite a horrific response to the illness, and wondering even where this stuff comes from, because prior to the emergence of science, when people would have just seen eruptions and maggots emerging from an individual's skin, how do you make sense of that? And we're going to talk a little bit about how people tried to make sense of things in our next module once we get to traditional healers, and we're looking at the past, the prehistoric, everything prior to the emergence of science. But even as we move into ancient physicians, they would not have understood this process. It wouldn't have been something that they were privy to. So this type of stuff, it caused a lot of questions for people as well as they tried to figure out what was going on. All right, we're going to leave it there. There's some material that's been posted on COVID-19 as well, a little more in depth on that subject. Once you're done the module, go on, take the test, and I'll see you in the next module. Okay, take care.